not only can we describe the motion of the body, on the left, we're describing the motion of the athlete, but we could also describe the motion of an object. A football pass in the air, that's curvilinear. Isn't it traveling in one direction? Each pass, it's not going to go front and back. So that object can be moving in a linear form. The football pass is moving in one direction at relatively one speed. Of course, it's going to be a little faster at one point versus another, but more or less the same speed. Okay, so as we're talking about other ways to describe motion, linear, a form of motion of a human body or an object moving in one direction at one speed. Parts of the body are moving together as a unit, and it can be rectilinear, movement in a straight line, curvilinear, movement in a curve or an arc. And then we have angular. So an angular form of motion would be motion around an axis. As such, it is not in one direction at one speed always, right? Not necessarily in one direction at one speed. The key here is motion around an axis. Let's go back to our pictures. Oh look, I even put it on here for you. I actually forgot I did that. There's some other information that I'm not going to ask you to know, but another word for linear is translation. You don't need to know that, but it's just FYI. In addition to rectilinear or curvilinear, sometimes you'll see a linear motion described as circular, but I'm not going to ask you about that. Angular is motion around an axis. Typically, motion is occurring at different speeds. Body regions may be moving at different speeds relative to each other. Kind of the opposite of linear. Do I have any examples on here? Okay. Angular motions are much more common. If we think about particularly American sports, these are much more common. What are some examples? I already gave you some. A football quarterback throw in terms of the athlete, football thrower, right? The shoulder is moving in one direction, the trunk is moving in another, they're stepping in the other direction. So body segments are moving in different directions, but also different speeds. When they cock back, there's kind of a pause and then an acceleration and a deceleration. A baseball throw. I mean, a lot of our sporting motions are angular. What are some examples of not sporting motions? What about, if you think about a physical therapy type example, maybe you've heard of the sit to stand test. What if I'm sitting in a chair and I go to stand up? That's angular. Some of my joints are moving in one direction, some are moving in another. My legs might be moving at this speed, but my arms are not moving as much. So it doesn't necessarily have to be, or picking up a box, okay? All right. So we have also linear versus angular. We are going to, my cat is getting right in the middle of my presentation here. We're going to be practicing this in lecture and also in lab. But again, same thing, the better you can learn it before we meet again, the more you're going to get out of it. Because, sure, it makes sense as I'm saying it, but when you come in next Thursday for lecture, you should be able to give these definitions, bar none. linear motion. You should be able to say movement of the body or movement of a projectile in one direction at one speed. All parts of the body moving together as a unit. You should be able to say quantitative, a way to analyze a motion using numbers. Angular, motion around an axis where there's different body segments moving at different speeds in different directions. Body segments are not moving together as one. That's the level of, really memorization that I'm looking for. And then once we meet again, we'll do more practice to even further cement it. And then, again, all these terms, oftentimes we can combine them, but I just want to make sure that you're able to define these. So sometimes we can use the terms static and dynamic to describe motion. I think you know what these are. Static. Static means more not in motion. Dynamic is in motion. Let's say at rest. Well, actually, I don't like to use the word at rest. I think a better way to do it would be not in motion. We can use these terms with balance. There can be static equilibrium or static balance. What if I hang you upside down and you close your eyes and you're just dangling there? You're not moving, you're not in motion, but doesn't your body still know that you're upside down? So even though you're not in motion, we can still discuss it and describe it and have a sense about it, versus dynamic is the study of something in motion. Okay, so I want to now go to the other terms. And these other terms are kinematics and kinetics. Kinematics and kinetics. So once again, we're providing more terms. We did qualitative, quantitative, linear, angular, static, dynamic. When we talk about kinematics versus kinetics, perhaps a better way of thinking about it. Up here, I purposely said these were to describe motion. If I wanted to really be specific, kinematics and kinetics would be ways to describe or study mechanics. I'm not going to ask you this delineation, but it's my job to be specific. So, typically we're going to see these more when we're doing more of a mechanical analysis. Not always, but okay. But here are the last terms that I want to introduce here in this video. Kinematics and kinetics. If you don't study, these are going to start to become alphabet soup in your brain, and more difficult and challenging. And then, when we meet again, and then I post another video, then you're going to have all this other stuff added on when you still haven't learned the previous. So I'm encouraging you to not get behind. I don't believe these to be very, very, very hard concepts. I'm trying to give you a definition as simply as I can, and I know absolutely that you can memorize them and learn them, and then after you memorize and learn them, we're going to apply them. That's my rah-rah speech. How did I do? Okay. All right. Let's go back here and talk about kinematics and kinetics. Kinematics and kinetics. Let's see, do I have another slide at the end here? If you don't mind, just one moment. Because I do want to, kinematics, I have so many examples, kinetics, okay. Sometimes I like to have a beginning way to just define them. So let me do that as well. The slides can get kind of busy, I think. So let's just straight up define these, okay? And they're in your notes. We have kinematics, and then we have kinetics. Okay, ways to describe motion, or if you want to be specific, mechanics. All right, here we go. Kinematics is the description of motion. I mean, a lot of times, where else did we use the word description? Qualitative analysis, so you see how some of these can overlap, okay? That's why I'm encouraging you to memorize them one by one at first. Kinematics is a description of motion, and I purposely gave you in your notes some things that would fall under this umbrella. I want to make a point. This can be qualitative or quantitative. So I know that we describe qualitative as a description of motion. Now we're kind of going a little bit deeper. So in this realm, okay, when we're comparing kinematics and kinetics, kinematics is a description of motion, and it can actually be qualitative or quantitative. It tends to be more of quantitative. So it tends to be more quantitative, but not always. You can see some examples, right? Distance, speed, acceleration, projectile. So it can be things that we typically thought of as quantitative, distance or speed. But I like, and I purposely put this on there, projectiles. Because didn't we describe motion already? We said that a motion could be linear or curvilinear. So that's an example of a description of motion that's kinematic, that's qualitative. So this could be, for example, let me use a different word here. A projectile we could describe as curvilinear, like a football pass, or rectilinear, like running in a straight line. So these would be examples of things that are qualitative. By and large, it's mostly quantitative, okay? But it can be qualitative. Acceleration, velocity, all these things. Now I want to jump ahead before I continue with kinematics, and maybe I want to give some more space here. Bear with me here. This is our last topic for this video. Okay. Because we can further subdivide the kinematics, right? Okay, get this to work here. We can have linear kinematics, or we can have angular kinematics. So this is where it starts to add on to each other, and it can be confusing. So please, 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 I encourage you to memorize these in order. All right, so, if it were me, I would just think, okay, right, kinematics is a description of motion. Kinematics is a description. And then we have linear. What was linear again? Linear was movement in one direction at one speed. So what is linear kinematics? Description of motion in one direction at one speed. What is angular kinematics? Description of motion that's around an axis at different speeds. And that's where we come to this. Linear kinematics. So kinematics, remember, is a description of motion. I said I was going to go ahead, but I didn't, so I acknowledge that. But we're just going to keep going forward here. Kinematics is a description of motion. Linear, in one direction at one speed, description of motion. Angular, moving around an axis at different speeds, description of motion. Be able to give one or two units. I think that's going to be an easier way to do this, to memorize, to learn. So I would encourage you to think of, be able to give some units. By and large, the linear kinematics have simpler units. Describing motion in one direction at one speed is a little bit more simple. So these would be units like meters per second. As you're going to notice, we're going to tend to use the metric system. Meters per mile, meters per second. What is the distance measure? Meters. So it could just be a straight-on distance motion, or it could be a distance over time. It could also be acceleration. Now again, if you were really a stickler, you would say, well, if it's acceleration, it's not one direction at one speed always. Remember I said more or less one direction at one speed. My cat's coming over to say, you have to say hi in the first video. You know, throwing, if we look at the projectile of a football in the air, there is going to be a little acceleration where at first it accelerates the ball, accelerates to a faster speed, then it slows down a little. But relatively speaking, it's more or less one direction at one speed with smaller accelerations. So I don't want you to get hung up on that detail. Whereas angular kinematics tends to be more complex. It's also more difficult to study. Okay? So some examples of units that you would see here. Think about rotation. Didn't we say that angular was movement around an axis? So think about units of measure that are going to involve more rotation. So what are some examples? Angular velocity. Whew, it's a mouthful. So I think about rotation or angular. Even degrees, right? Degrees, like range of motion degrees. It's around an axis. But more complex. It could even be like angular acceleration. See that on your notes there? If it was just acceleration, it's going to be a measure of linear kinematics, mostly. But once I add that angular or rotational, you're going to automatically think angular kinematics. We are going to give all sorts of examples in lecture and lab. If I go back to the PowerPoint, I give you some examples. You don't need to know these specifics. This is a tricky one. Let me go back. Let me just make sure I correct myself. Where was it? Oh, it was on here. You know, I said here range of motion in degrees. That's kind of a sticky wicket, as they say. So I'm going to take that out because I don't want to. It depends on the situation. Range of motion could be linear or it could be angular. But for ease of our discussion, let's just go with these examples. My apologies. So I've given you some examples here. A kinematic analysis of the shoulder and the elbow. If we're looking at the joint angle, that would be considered kinematics. If I was looking at something else, it might be kinetics, but this is kinematics. Acceleration. Wasn't acceleration something we talked about with kinematics? Let me go back. Acceleration is usually a linear kinematic. Now, it could be angular, right? So it depends. If you see if it's just acceleration in meters per second, linear. If it's acceleration, angular, then it's going to be an angular kinematic. We are going to be practicing this in lecture and lab. I include some examples in real life just because I think numbers are cool, but I'm not going to ask you these specific numbers. Check it out. Angular displacement. That moves it from a linear kinematic to an angular kinematic. We can look at the angular displacement of a curveball. That's the movement of the projectile. That's angular, movement at different speeds around an axis. Okay? All right. I want to end here by looking at the other example. I just have my notes here, pardon me, to make sure I'm following along. And I want to talk about kinetics. Kinematics was the description of motion, and it could be linear or angular. Kinetics. I've got a simple thing for you, okay? Stay with me, folks. Study of forces. When you see that magic word, you're going to think kinetics. Speed, displacement, velocity, acceleration. Those are all kinematics. When we have something that involves force, I'm banging on my dining room table. When we have something that involves force, it becomes kinetics. Now, it doesn't necessarily just mean that we're talking about pounds of force. That is a simplest example, right? What's the simplest example of measuring a force? We can measure the pounds or newtons. Newtons would be the metric system measure of force. Newtons of force. But it's not just straight on measurement of force. And that's why I've given you some examples in your notes. Inertia. I know we're dangerously edging close into physics territory, which, believe me, I do not like. Maybe you do, I do not. But inertia has to do with the force needed to move an object and or keep it moving. Things to consider with kinetics, inertia. We have to consider the mass of the person or the object. Things to consider. We have to consider the force. We have to consider the base of support. So these are all considerations. But I also want to introduce torque. All right, torque. You ready for my simple definition? Either rotary force, or you can think about it as force around an axis. Whichever sinks into your brain better. You may have to force it in there, but you're going to sink it in there. Rotary force, force around an axis. Torque. One of the easy examples is using a wrench. You move the wrench in a circle, right, around an axis. Yes, there is actually such a thing called a torque wrench, where you can generate more torque. We're going to talk much more about torque, but this is something involving forces. So there are key words for kinetics. The key words are force and torque. When you see those words, you're thinking already of a kinetic analysis. Okay? These are the things that are considerations for torque: inertia, mass, force, center of gravity, base of support, torque. Torque is rotary force or force around an axis. One of the best examples would be the torque or rotary force developed at the elbow during a baseball pitch. There is a twisting rotation around an axis there. It's a very violent force, but it's capable of chucking a ball really far with a lot of spin. Technically, torque is equal to the force multiplied by the perpendicular distance from the force line to axis of rotation or movement arm. You don't need to know that. I may give you some examples, but you don't need to know that. You do need to know the definition of torque. You do need to know the units, Newton meters or foot-pounds of torque. We're going to talk much more about this. Here's an example. I mentioned the elbow pitch. During that late cocking phase of a baseball pitch, windup, the torque on the elbow can be as much as 64 Newton meters. I know it doesn't mean much to you, but studies have been done where they take a dead person, a cadaver, and they put that force on the ligaments of the elbow, and the ligaments of the elbow will break after 32.1 Newton meters. So we're putting on even more. Yes, we have muscles to help defray some of that force, but that torque is an incredibly violent motion. If you want, here's an example of how you would measure it. This is a wrench. I'm not going to ask you to measure something like this on a test, but if you're curious, here's the wrench, here's the axis or the nut I'm trying to move, and then I have to use my force to try and move the wrench, so we can measure the amount of force it takes. Let's just say it takes 50 newtons of force to move that wrench. And then I look at the distance between what I'm trying to move and the force. That's the moment arm. You measure them, you get your Newton meters of force. We can do the same thing at the elbow. The force would be the red line. The distance from the effort would be the blue line. We could measure it. Lastly, before I leave you, is just to mention type of loads. This technically falls under a kinetic analysis. Force, load. We can have a compression, a tension, and a shear. These are the most important, most common ones. Make sure you can define them. A compression force is a force smushing something. When you're standing, isn't there a compressive force on your knees? Because the weight of your body is compressing the knee joint. Tension is the opposite of that. Tension is when there's load pushing things apart. Think about that gymnast rotating with, a gymnast is going to be holding on to the bar with their hand and their shoulder. But as they spin around that uneven bar, it's a tension force on the body. Shear is a side to side or twisting. ACL tears are commonly happening because of a twisting or shear force. Not necessarily straight up and down compression, not necessarily straight up and down tension, pulling apart, but some kind of combination of a twisting, which usually involves some compression and some tension. And of course, oftentimes these loads are combined. If you're looking at the complex motion of a baseball pitch, at some points we can have mostly a compressive load. At other points we can have mostly a tension load or a shear. So usually we tend to have many different ones. I give you some examples here. These are some shearing forces. I just wanted to put some numbers here. I'm not going to ask you these numbers on a test, but look at how many, and this is also a way for you to see how the units, newtons and pounds of force. Remember, anytime we see force, are we thinking about kinetics? Look at the shear force on the shoulder. Look at the shear force on the shoulder during deceleration, 90 pounds on average. That's a lot for the shoulder, which has a relatively small socket, doesn't it? The glenoid cavity is pretty small. What are some considerations with kinetics? Mass. Back in the day, C.C. Sabathia, big dude, right? So he was able to rely on the mass of his body to help him propel the ball. Tim Lincecum, skinnier dude. So he wasn't going to be able to rely as much on his mass. So he had to rely more on his torque and the use of his lever arm, right? There's all sorts of ways you can measure this. You don't need to know this. One way to measure force is mass times acceleration. You don't need to know these. I'm just giving you some examples. I wanted to give some real life examples. Look at this, a 98 kilogram running back. What is that in pounds? So 98 kilograms, we would take 98 times 2.2, right? 98 times 2.2. That's a 215 pounder. So a 215 pound running back accelerates to a speed of 22 miles per hour within 2 seconds. How much force is required to stop him? God bless the linebacker or whoever is trying to stop. I mean, this picture I think is Adrian Peterson, but look at that. In order to stop that amount of weight at that speed, that force is 1,921 newtons of force, or 432 pounds. This defender has to provide 432 pounds of force to stop that dude, right? How about that for some numbers? Okay, I'm going to end there. I've given you plenty to study. Please study, please study, please study. We're going to be practicing this in lab and in lecture, and then moving on. All right, great job, folks.